Not eat on camera. All right, how's it going, everyone? Another day, another dollar. We're going to be talking we're going to be finishing our discussion on rational expressions today. Rishi's going to finish that up, and then we're going to move into some stuff about polynomials, factoring them, long division, all the good stuff. And yeah, it'll be a blast. We're still kind of in material that it seemed like people felt pretty okay on. So we'll just be moving through at a, you know, brisk-ish pace. Um, and hopefully it'll go smoothly. As always, I want to extend the offer. Anyone who has a question during the course of today can definitely just unmute and interrupt us. Um, you can also raise your hand, type something in chat. A reminder that we have office hours. I have office hours before section, every day at 1:30 p.m. And then Rishi has office hours directly following this at 4 p.m. Pacific time. So that's a good opportunity. If anything doesn't click today, you want to get some confirmation, anything like that, come to either of those office hours. We'll be more than happy to have you. I won't dwell on it too long. I'm seeing familiar faces, so it's everyone kind of knows the deal here. If you're new and this is your first section, welcome. Um, we can let me first post the link to the Discord. If you're not in the Discord, I highly encourage you all to join. It's where we've been posting our worksheets. But we will also post the worksheet in the chat as well. So here is the Discord link. So if you're not in there, join up. And then I will upload the files of the worksheets we're going to do today.
All right. Thank you, Nick. Great introduction. I got all the bases covered. This is great. Um, Thank you for those of you guys who came to our office hours yesterday or today morning. Um, Good to meet some of you guys, and thank you for being here. Um, First thing I'm gonna do is share my iPad, and we're gonna get into more rational expressions. We're not gonna spend a super long time on it, as Nick was saying. It seems like you guys have a fairly complete well, understanding of rational expressions, which is good, right? This is all preparatory, and so if you're feeling good, we're just going to move on onwards. Okay, let's see. The screen and cool. Let's jump into it. So here we go. So the third module for rattle, or rational expressions, is going to be dealing with inequalities and then drawing rational equations. So as a reminder, the first module was dealing with proportions and things like that. And then our most recent module from the end of yesterday was talking about, how you can multiply and divide, and do different operations to fractions. And so we're just going to pick up where we left off. So the first thing I want to talk about is the domain of functions. Just a quick little vocab thing. Uh, the domain of a function is extremely important for inequalities, especially. So pretty much what that means is when you have a graph, the domain is parts of the graph which will actually have values that are valid. Um, Usually you can have values anywhere. So, you could plug in a value for X and you'll get a value for Y, no problem, right? However, there's a there's an example here, or I'll just use some blue to make the colors pop. Um, there's an example here with 1 over x, where you can't actually have x be 0, right? So the domain for this equation is going to be x equals 0, or rather, x doesn't equal 0, because that'll make the equation invalid. And so the domain of a function, long story short, is just trying to figure out what are we working with here, right? Like what values of x can we have? That's just a little bit of vocab, nothing super mind-blowing. Next, I want to talk about solving rational inequalities. Um, so when we have an expression solving a rational inequality, first thing we're going to do is factor. If you need a refresher on how to factor an inequality, definitely take a look at the solutions for the rattle section, which were also which was covered yesterday in that Zoom recording, which is posted on YouTube. Check out our Discord resources channel if you want to go and watch previous sections of this session. But first thing you're going to do is factor. And then this is where domain comes in quite often, is we need to look at the denominator of a fraction. So with rational functions, you cannot have 0 on the denominator, right? Anything divided by 0, it is invalid. You just can't have that in math, right? I remember, like, wondering why is that um, not possible? Why can't you divide by 0? And it's like, well, if you have, 6 oranges, you divide by 0. Like, what does that even mean, right? It just isn't something that you can have in real life. And so in math, we just say there's no solution in that case, or it's a invalid solution. So all we're going to do to make sure that we have the domain, properly looked after is make sure nothing in the denominator will lead to 0. So we pretty much set x to be anything but something that will give us a 0 in the denominator. Cool. Then I want to talk a little bit more about uh, our intervals. So how do we write the domain in interval notation? Yeah, great question. So the next example is a little bit more complicated. So first, I'll try to answer your question for this first part here. So going back to the very top, if someone were to give us this equation, y equals 1 over x, the way we would write the domain would just be negative infinity and all the way up till 0, but not including 0, which means we're going to use this kind of parentheses sign. And then we're going to say u. U means union. It's just a way to like say and in math. And 0 all the way until infinity. So that's how we write the domain for the domain in interval notation, as was asked in the chat. This the infinity and the negative infinity, you guys will know, also have a parentheses sign, and that's because infinity isn't a number. So you can't like include infinity when you're describing domain, because, well, it's not like a thing that you're including in there, right? You could never plug in infinity into your equation, right? We're not talking about a million or 100 billion. We're talking about infinity. It's not a valid number. Then the second problem, kind of a similar deal. We're really just going to be using these parentheses signs as the norm. And then in a later example, we'll see that a bracket, just like this, a bracket will mean that we do include the value there. So let's say the function was a domain of 0 and onwards. We'd say 0 with a bracket, comma, infinity with a parentheses sign. So that's referring to open or closed um, domain, right? So the zero with a closed bracket means you include that zero, and the infinity with a parentheses means it's closed. Or I might have switched that around. Sorry. You include the zero if there's a bracket, and you don't include infinity if there's a parentheses sign. But anyways, good question. Good question. And next, I want to talk about how we're actually going to get our domain for this, for the domain for this. Okay, cool. Yeah, thank you, Nick. Yeah. Parentheses sign is open, bracket is closed. There we go. I think I said it backwards for some reason. Um, awesome. Always on top of it, Nick. Thank you. I appreciate it. So anytime we're looking to see what the domain of a function is, we're going to have to test which intervals uh, are the numbers going to be what we want, right? And that kind of depends on what our inequality or our equation is. And so this problem here, we have a greater than sign. We're pretty much saying, okay, we have this rational expression, and we want whatever we plug into x, whatever we plug into that rational expression to be greater than 0. So to find out what we can use domain to find out what x is, right? So x is going to be a range of values. It's not just going to be one number or two numbers. It's going to be a weird kind of mix of numbers. And so we're going to use domain to our advantage. So first, we're going to kind of get like our points of interest, for lack of a better term. So anything that would kind of result in these factors going to 0. So when we look at our final factored inequality, our what are we going to plug in for x to get 0 for any one of these factors? That's what we're going to use as our points of interest. So for this first guy, x plus 2, let's say x plus 2 equals 0. Therefore, x would equal -2. So that's going to be a point that I'm just going to want to write down, take note that it's important. Same thing, x equals -1, x equals 5, and x equals -5. And so those numbers are all listed out here. You can essentially solve for 0 in each factor, and that will give us x values that do not satisfy the inequality. The reason they don't satisfy the inequality is that if either any of those numbers in this inequality were to equal 0, then the entire thing would either become 0 or no solution, right? And so since we're looking to see it's greater than 0, right? It's greater than sign right here. Those would be invalid solutions. Any questions so far? I know it's a lot of talking, but I just kind of want to explain why we're doing these steps and not just what are the steps, right? Cool. Well, moving onwards, once we have those points of interest, right, all those numbers that make the factors go to 0, both in the denominator and the numerator, you'll note, we are going to do a little number line business. And so this is all kind of already done out, but essentially what this is taking each of our numbers. First we write them on a number line. So take a number line, write out your numbers. And I've kind of already done that beforehand, but we have -5, -2, -1, and 5. And you'll see they're kind of color coded, right? So this is the row for -5. This is a row for -2. This is the row for -1. This is the row for 5. You'll see there's a bunch of pluses and minuses. So the way to figure out what our solution set is going to be, to figure out how to make that polynomial greater than 0, is we test whether each of those factors is going to be positive or negative. So essentially, we will plug in each of the numbers, each of our points of interest, these 4 numbers, and plug them in to see whether our polynomial ends up, or not our polynomial, whether the factor ends up being positive or negative. And so -5, if we were to plug it into, I guess I should, yeah, here we go. X minus 5, x minus 2, x minus 1, x plus 5. Cool. So if we were to plug in -5 into x minus 5, we would get a negative sign. If we were to plug in some number between -5 and -2 into x minus 5, we would get, sorry, I'm gonna feel like well, if we were plugging that, we would get a negative sign. All right, I guess I'm switching around the order here. Let's see, -5. I think I flipped this around here. I believe. Let's see. Trying to figure out my mistake. 1 second.
Uh, swap the 5 signs. Swap x minus 5 and x plus 5.
X, just the 5, or I think
I can't tell if the
yeah, I swapped something around. My apologies. My apologies. Hmm. X minus 5. Yeah, it should be. What's there? Minus there. And then I'm trying to see these two. I think I just switched the sign of everything. Let's see. All right.
oh yeah, the factors in the fraction are x plus 2, x plus 1, x plus 5, and
Okay.
x minus 5.
Okay. Okay. Cool. There we go. Okay. Yeah, my mistake, everyone. Thank you, Nick. Cool. So that should be good. So let's see. X plus 5. Yeah, okay. That should cover it. So starting from the beginning, once we reached right out our factors. Yeah, I guess I copied them from memory, so my mistake there. You copy down the 5 factors or from your inequality up here, and then you write down the the number that would make that each of those 0 down here. Right. So the signs would kind of be flipped, for lack of a better word. But once you have that, what you would do is plug in a number less than -5, and that'll get you a negative number, and then a number between -5 and -2. So let's say like -3, which would give you a positive number if you plug that into x plus 5. And then let's say you plug in a number between -2 and -1, such as in this case, which would give you a positive number. And any number beyond that, I mean, you can kind of tell already that if you were to add anything that's larger than -5 into x plus 5, you would get a positive. We'd do the same thing for x plus 2, x plus 1, and x plus 5. The reason for that is because what we care about is our sign of things, right? Because our problem is asking us uh, when can we have a case, what are the cases which makes this polynomial greater than 0? And so what we do is we find all these signs of these polynomials on the left here, and then we find the signs for in between our various points of interest. And then what we can do is go ahead and multiply our numerator signs together and divide by our denominator signs together. And so our polynomials, I'll kind of as a reminder, I'll write down here are x, let's see, x plus 2 times x plus 1 divided by, we're running out of space here on the margins. X plus 1 divided by x minus 5 times x plus 5. So what we're going to do to find the sign of any number which you were to plug in the number line, so like any number anywhere, is we would divide the x plus 2 and x plus 1 signs, and we divide by the x plus 5, x minus 5 signs. And so we would, to find out whether a number that we plug in for x is, like, let's say less than -5, we would multiply the sign of x plus 2, x plus 1, which is a positive sign, and we divide by the signs for x plus 5 and x minus 5. So it'll be a negative times a negative divided by a negative times a negative, which is a positive sign, which is why there's a positive down here. Feel free to, interrupt if there's any questions or, I make a mistake or anything like that. But moving onwards, we will divide to find this, the sign of this right here. We're going to go ahead and multiply the signs in the numerator. So that's going to be x plus 2 and x minus 1, or x plus 1. So that's going to be a negative times a negative divided by a positive times a negative, which is going to end up being a negative value down here. Same thing up here. We're going to, between -2 and -1, we're going to go ahead and multiply a positive times a negative and divide by a positive times a negative, which will get us a positive. And same thing for these two. We're going to do positive divided by positive times a negative, which will get us a negative. Last but not least, any number greater than 5, we're going to do positive times a positive divided by a positive times a positive, which will get us a positive. So I know that's a lot of signs, but keep in mind here, this is a huge polynomial. I mean, we're getting like factor, x to the power of 2, and then x to the power of 1, and then a coefficient on the top, right? X squared, 3x, and 2. And on the bottom, we have x squared and then coefficient. So the point being, there's a lot of different numbers we could test. With all that said and done, we finally have our answer. We have finally tested every single number on the number line. The way we're going to write our answer is going to be, well, what are we looking for, right? I like to remind students in a time like this, what are we doing? We did a lot of work. I made a mistake at the beginning. We're all bogged down. What's the question? The question is asking us, for what values is this polynomial greater than 0? So to write our answer, we're just going to write out our positives. So this is a positive, this is a positive, and this is a positive. So to answer the question, which numbers of x, which values of x will get us that polynomial to be greater than 0, we're just going to go ahead and write out in interval form, interval notation, from -infinity to -5. And we can kind of write a u, and then write our next interval, -2 to -1, which is referring to this guy right here. And then we can write a u, and then write 5 until infinity. And so you might be wondering, well, why don't you write the closed brackets, closed interval, right, using this? The reason for that is the question is asking us greater than zero, right? Greater than zero and not equal to zero. So if we wanted to get equal to zero, then we might be including like -2 or a -1, anything like that. But we're not going to be including those in this answer because we're looking to see what's greater than zero, not equal to zero. And so that'll be our final answer. I'm going to go ahead and box that. And yeah, any questions with that? Cool. Well, thank you for the help, Nick. That was a tough problem, I will say. And I'll tell you guys, for those of you who are here or watching at home, these are the kind of topics that um will really test you on the MPE, on that math placement exam. And so, if you're able to handle this problem, seriously, like hats off to you. This is a tough problem, and so you can carry through and do a few more examples with this. And if you're able to handle this, then you guys are gonna nail it. All right. So continuing onwards, just a few more vocab words. We're done with the brunt of the information, but I just wanted to cover quickly what asymptotes are. So first things first for a graph, as a reminder, this might be review for some of you, maybe not for others, but zero is where y is zero and there's an intercept on the x-axis. So pretty much where does the graph cross the x-axis, the horizontal axis? Those are called zeros. Vertical asymptotes are vertical lines which the graph approaches. So you can kind of see this graph, this equation starts to approach a vertical asymptote at x equals zero. So this asymptote right here. However, it never crosses that line. So an asymptote is like when you're almost there, but not quite. So these could be found at x equals zero. They could also be found at other values of x, but it's always going to be a straight vertical line for vertical asymptotes. But we also have horizontal asymptotes. So there's kind of three little rules I like to say for horizontal asymptotes. Horizontal asymptote, just as a quick note, is the same thing as a vertical asymptote, but horizontal asymptotes are sideways, right? So it's going to be a line going across the page. And the three rules are: if the degree of the polynomial is greater in the numerator than in the denominator, then there's no horizontal asymptote. The degree of the polynomial, by the way, refers to the power of x. So let's say we have a polynomial like x squared divided by x, 3x maybe. This is something you could simplify, but let's say that's the start of the thing. So it could be like x squared plus 2x and then 3x plus 1, some random equation. Essentially, if the highest power of x is greater in the numerator than the denominator, there's no horizontal asymptote. If the degree of the polynomial is greater in the denominator, then we have an asymptote right at y equals zero, which you can see pictured here. And then if the degree of the polynomial is the same, so let's say it was like x squared plus 3 divided by 2x squared plus 2x, then we would have the horizontal asymptote is the ratio of the leading coefficients, which pretty much means what is the coefficient of the numerator's highest power of x? So that's going to be a 1. And then what's the denominator's leading coefficient, which is going to be a 2. So here it'd be at 1/2. Y equals 1/2. Cool. Any questions? Just three little vocabs. We just did zeros, vertical, and horizontal asymptotes. Cool. Well, good news, guys. Rattle, rational functions. We're done with all the materials. So real quick, I want you guys to take a look at 3.1 and 3.3 and just go ahead and give me a thumbs up if you feel like good, you feel good on this. You don't want me to spend a ton of time on it. You'd rather see more stuff about polynomials that Nick's going to cover, and then give me a mouth open emoji if you want me to spend a little bit more time. You want me to really dive deeper into these two problems. And also note, guys, you can always check the solutions later, and then I'll kind of give you a preview. There's also the problem set down here, which you can kind of do as homework, if you will. All right. So any input? So mouth open emoji means you do want me to spend more time. Thumbs up. You don't want me to spend. Okay. Cool. So I'm getting kind of a mix. So I'll take that, kind of average it out, if you will, and I'll cover these, but I won't spend a super long time on it. Right. All right. So Rattle 3.1 is just kind of talking about domains. So what I said kind of at the very beginning of today, how can you find the domain of any expressions? What I'm going to go ahead and do is, just for the sake of time, is I will cover part A. So I'll do 1, 2, and 3 for part A. But I recommend, if you guys are feeling, extra, confident, or you have some time, or, whatever it is, go ahead and do B and C on your own. I'll just do A for the sake of time. So for A, we have to first determine determine the domain of the expression. The way we're going to do that is make sure that the denominator is not equal to 0, right? That's pretty much the only thing that will make our domain become not all real numbers, right? The domain of a line, for example, is all real numbers. There's not any there's nothing that's like discluded from some random line that you draw across your page, because it could have x values from negative infinity to positive infinity. However, here what we're going to do is make sure x squared minus x minus 20 does not equal 0. That's going to make sure that our domain stays true, right? What we're going to do is factor. It's always a good first step, guys. Every time you see a polynomial, go ahead and factor it, or simplify it, if you will. Factors are going to be x minus 5 and x plus 4. The way I kind of found that real quick is just to make sure that this negative 5 and this 4, if they were multiplied together, you should get 20, or rather negative 20. And then if you were to add them together, you would get negative 1, which is the coefficient for this right here. So this is essentially a negative 1x. So remember, this b value, if we're using the ax squared plus bx plus c, essentially you want the c value to be your two values here multiplied together, and then you want your b value to be those two added together. But anyways, if there's any questions about that, please let me know. What we're going to do is make sure that this statement is true, right? X minus 5 times x plus 4 does not equal 0. So solving for x does not equal 5, x does not equal negative 4. That is our domain.
Rishi, I think
Yeah.
there might be an issue if you factor the top. One of those might cancel.
What do you mean issue?
Like, okay, if you factor the top,
Mhm.
the numerator, you're gonna get x minus 1 times x plus 4.
Yeah.
And if you have x plus 4 on the top and bottom, it cancels, and I don't believe it actually matters that it equals zero in the denominator. It's a removable singularity.
Interesting, interesting. Okay.
I'll double check that.
Um,
I'll double check that. But
yeah, I'm very curious. That's a, that's a really good point. Why don't we whip out Desmos? I'll
I am
continue on.
actively whipping out Desmos.
Okay, okay, awesome, awesome. Okay, and Keanu in the chat and Angelica are saying that there's a hole, which means that there wouldn't be
It
a
might
point
be.
there. Cool. But guys, I'm really glad we're thinking about this. Um, I'll just continue on with part two for now, but yeah, let's see what that looks like, Part two is just simplifying the expression. So Nick already said it. Essentially, we're just going to find our two factors for the numerators and for the denominator. So it's going to look like it's going to look like x plus 4 times x minus 1 divided by x plus 4 times x minus 5. And then
You
it
guys
says
are right.
simplify the, yeah.
You guys are right. I'm a math noob.
Okay,
It does
cool.
leave a hole. It doesn't affect what the graph looks like, but there's just a
Sure.
hole in the middle of it.
Uh-huh, uh-huh. Yeah, well, that's why the problem says simplify the expression, but still find the domain, right? Because that way we can note that even when we cancel these two guys, we're going to end up with a simplified expression x minus 1 divided by x minus 5. However, with the caveat that x cannot equal -4, even though x plus 4 doesn't appear on this denominator here, right? We got rid of it, we canceled it, but it leaves a hole. But good. Thank you for bringing that up, Nick. I do appreciate it. Um, that's part two. Simplify the expression. So we're just going to go ahead and box that guy right there. X minus 1 divided by x plus 5. Yep, looks good. And then last but not least, evaluate the expression for the values given. So for this problem, we're given -3, 0, and 3. So we're just going to go through point by point. X equals -3. We're going to go ahead and plug that in to this expression over here. So if x was -3, we'd get -3 minus 1 divided by -3 minus 5, which will get us -4 divided by -8, or 1/2. X equals 0. Will be 0 minus 1 divided by 0 minus 5, which will get us 1/5. And last but not least, for x equals 3, we are going to go ahead and plug in 3 minus 1 divided by 3 minus 5 to get 2 over -2, which is known as -1. There we have it. Part one done. Or, well, part one, 2, and 3 are done. I should have said part A done. A little bit confusing with, we got both 1, 2, 3, and ABC. Any questions with that? Cool. Well, good job, those of you guys in the chat, and also Nick, thinking ahead, seeing if we have a hole, which we do, which is important for graphing, guys. It's important to know, like, what do these things mean, right? We're not just doing this for fun. We're doing this because these tools would probably help us graph this expression, right? Which is what we get into in Rattle 3.3. So essentially, I'm going to go through this entire chart. I've just kind of created a skeleton to write out what our horizontal and vertical asymptotes are going to be for 4 different expressions. So these are 4 different expressions that have kind of like they're all rational, except they all have different kind of formats. They all look a little bit different. To answer the question of what their horizontal and vertical asymptotes are, I'm actually going to start with vertical asymptotes because it's easier, and I want to get done with it uh, as quickly as possible. And so I like to just start with the easy part first, which is make sure that the denominator of each of these does not equal 0. So we're going to have a vertical asymptote at x equals 3 for the first one. And for the second one, we're going to say x minus 1 does not equal 0. And x minus 4 does not equal 0, which should get us x equals 1 and x equals 4 as our two vertical asymptotes. Then for our third equation, we're going to make sure that that whole denominator does not equal 0. The way I'm going to find out what x is, because you can't really plug in x when you have x squared, you want to factor it out first, for an asymptote at least. What I'm going to do is just multiply it out to be x plus 1, and then x, or I'll write it out, x squared plus 2 over x times x plus 1, x minus 1. And so x plus 1 cannot equal 0, and then x minus 1 cannot equal 0. And then don't forget about this little x over here. X cannot equal 0. So we're going to have our asymptotes are going to be x equals 0, x equals -1, and x equals 1. If anyone needs me to refresh on how I'm finding all of these, please let me know. I'm just going quicker for the sake of time. I know some of you guys wanted to look at polynomial equations today. So last but not least, we've got this. Actually, it might be the least. This last one seems pretty easy. X cannot equal -1. So our asymptote is going to be x equals -1. And you'll note that the reason I'm writing out equals and not does not equals for all of these is because in asymptote, you're graphing a line, right? You're graphing what that dashed line. Asymptotes are usually going to look something like this, a dashed line. And so I'm going to go ahead and write an equal sign because it's an equation, right? Like, what is that asymptotes equation? Cool. Okay, well, if there's no questions, moving on to horizontal asymptotes. As a refresher, I'm going to go ahead and look at my rules, right? I don't have these rules memorized, and so I'm just going to pull up my handy dandy little cheat sheet. The first rule is if the degree of the polynomial is greater than the denominator, there's no horizontal asymptote. So we're looking for the top, the numerator degree being greater. So I'm looking down here. There's only one case where that happens, and that's the fourth case. Rule 1, no asymptote. I think I spelled that right. Correct me if I'm wrong. Next, we're going to look at rule 2 and rule 3 to see which one of these has the denominator being a greater case, a greater degree. Denominator has a greater degree, then there's going to be a horizontal asymptote at y equals 0. Looking back down, that's only going to occur, let's see, in the third case down here. So rule 2, since we have a greater degree of polynomial in the bottom, then that means the bottom is going to result in a polynomial, or in a asymptote, horizontal asymptote of y equals 0. And then we can kind of clearly see that these first two, both will follow rule 3, which, as a refresher, means or says that if the degree of the polynomial in the numerator and the denominator are the same, we have an horizontal asymptote at y equals 1, or rather y equals the ratio of the leading coefficients. Okay, so that's going to be 1 over 1 here, and this is going to be, it's going to be 2 over 2 uh, for the second one, which will both result in an asymptote at y equals 1. Cool, cool, cool. So maybe I do have the rules memorized, or at least I had rule 3 memorized, seems. All right. Any questions? Any questions? All right. I definitely recommend that you guys take a look at this problem set. The first one, I'm not gonna lie, guys, it's pretty easy, but the second and the third one are very, very useful. So the second one involves, practicing all these rules of like asymptotes and graphing and intercepts and just common sense, just like how can you kind of work your way through a problem. That'll come in handy, if they ask you on the math placement test, like which of these graphs is the right graph or something like that. And then this third one, solve the following inequality. Is exactly like that problem with all the plus minus, plus minus, plus minus, all that business with the number line that I did earlier, which I made a mistake on. And so it's a hard problem, guys. It's a hard problem. Take a look at it. If you're going to do some homework tonight or tomorrow morning, definitely take a look at problem 2 and problem 3 from the Rattle problem set. Solutions are posted in the Discord. And with that, I'll pass it over to Nick.
All right. Sounds good. Well done, Rishi.
Thank you,
With
thank
that,
you.
we finished the second of our 6 modules or 6 topics that we were trying to finish. So that's pretty cool. And let's move right into the third one. So we're going to talk about polynomials. It very naturally kind of follows up after talking about rational expressions. There's the same kind of concepts of factoring out binomials, finding holes in graphs. Mainly today we're going to talk about finding factors of larger polynomial expressions and some of the ways that we can do that. I'll go ahead and share my screen on my iPad. Okay, cool. So, oh, goodness. That's terrible. I think I toggled on a setting that I don't want on.
What
Hold up.
happened, man? What happened?
I think I
Oh
toggled the
wait,
wrong setting.
I think it might have been good for a second. I might be wrong.
We'll see.
Okay, okay.
Okay, what about now?
Great. That's
Yeah.
great. Yeah.
Okay, cool. All right. So, the first thing we're going to talk about is first I want to say what is a polynomial? It's any sum of terms containing some variable x to different degrees. So like Rishi said, the degree of a single variable is the exponent it's raised to, and the degree of a polynomial is the exponent of the largest degree term. So in this case, this first expression, for example, we are multiplying 2 degree 2 polynomials, which is going to give us a degree 4 polynomial. And the easiest way to multiply them together is similar to just using the distributive property. You know, if we wanted to multiply 3 times 4 plus 5, right, then we can distribute that coefficient on the outside to get something like 3 times 4 plus 3 times 5, right? Same thing we do with polynomials here, where we are rewriting this expression as each individual term multiplied by the whole thing, like so. And then from there, you can just distribute in and combine like terms. Add up all the squares, add up all the just x's, add up all the constants. You may have heard about the FOIL method. This is specific to multiplying two binomials. And FOIL stands for first, inner, outer, last, which means that we're going to end up adding four things together. The first thing that we're going to do, we refer to as first, because we take the two first entries in each one, multiply them together, and that gives us our first term. Then we have inner, where we take the two terms that are on the inside, right next to each other, multiply those together, that gives us our second term. Then we can take the two that are on the outside, the outer terms. So in this case, x and 3, multiply those together, that gives us 3x. And then finally, we have last, where we take the last entry in each one. In this case, 2 times 3 is going to give us 6. Then, taking those four terms that we got, we just add them together. So we end up with x squared plus 2x plus 3x plus 6 is going to give us this x squared plus 5x plus 6. And that is how I was taught to multiply binomials. That's how I think a good portion of us, I mean, put a reaction in chat if you heard the term FOIL at some point in your math career. I have a feeling it's probably a good amount. But really, fundamentally, what we're doing is this distributive thing. Okay. Now, the inverse of multiplication, as we know, is division. And so if we're multiplying binomials into an expression, there has to be a way to factor binomials back out of an expression, right? And the way we do this is super similar to typical long division, the way you're first taught to divide, where you have some number that you are trying to, the larger number that you're dividing, and then the divisor, or the small number that you're breaking it into groups of. And then you essentially find some multiple of this guy, the largest multiple of this guy that will go into these first numbers. In this case, 2 times 9 would give us 18. 3 times 9 would give us 27, which is larger than 24. So 2 is the number we write, and we write 2 up here. We then subtract this result from these first two numbers, getting us 6 in this case. And then because this number is too small for 9 to go into, we drop down the next digit, which is a 3. Then we see that 9 times 7 is exactly 63, and subtracting would leave us with no remainder. This is how we've typically done long division in the past, and it's a super similar concept for polynomials. And it's something that I kind of wish I memorized after I learned it the first time, because it's surprisingly useful, and not a lot of engineers actually remember how to do it. So you would have a leg up on the other engineers. So the way it works is basically instead of having just one number that you're trying to find a multiple of, you have some polynomial out the front. And you want to find the multiple of this polynomial that allows you to cancel the first term of this polynomial with the first term of the dividend, maybe? Is that the word inside? I don't remember. But yeah, so in this case, we want to divide 2x minus 3 into this, we want to cancel that 2x with the 2x to the fourth. The factor that would allow us to do that is if we multiplied it by x cubed. So we multiply this whole thing out front by x cubed, and then subtract that from these first two terms. That's going to leave us with another term. In this case, this minus 6x cubed. And then because we need two terms to match up with our divisor, we drop down this next guy and do the same thing over again with the goal to cancel this first term. That'll just be a process that we can repeat over and over until eventually we, hopefully, if this number is a perfect divisor of the polynomial, in other words, if 2x minus 3 is a factor of this polynomial, we'll end up with a 0 remainder at the bottom. So we perfectly put it into this large polynomial, and the remaining polynomial up at the top is the result after the division. In other words, 2x minus 3 times x cubed minus 3x squared plus 6x minus 4 equals this big guy that we were working with initially. Okay, so we basically just removed the 2x minus 3 and we're left with this polynomial here. Yeah. And if you do have a remainder, by the way, so say this number is not 0, it's some constant at the end, then you actually just have an extra term here. That would be whatever that constant is divided by the divisor. So if this wasn't 0, that was c, then you would have an extra term there. And that just means that you didn't find the perfect factor, but this ends up being, this ends up working out. Okay, cool. So that's one way to divide polynomials. I'd say in general, that's the more robust way. That's the way that's easier for me to remember. But there's another way to do it called synthetic division. That works like this. So first of all, who has heard of the long division of polynomials at some point? Because I had, okay, good, cool. Perfect. All right, good. Who's heard of the synthetic division? Because I think I have, but I think it was buried somewhere deep in my brain. Okay, cool. All right, well, that's good. Another one? Yeah. Okay. All right. So as a quick overview, yeah, exactly the same. Same as me. Never actually used it. So the first step is if we have some big polynomial that we're trying to divide, this is our divisor. The first step is you flip the sign of this guy. So we have a positive 1 here with a negative 1. Fair enough, yeah. And honestly, they both work. It's just up to you guys which preference you have. The main engine behind synthetic division is this table shape right here. So you're gonna draw this T table shape where up here we put that flipped sign divisor, and then here we put all the coefficients of our polynomial. Then from here the method goes first drop down the first coefficient. We don't do anything to that. Then we multiply the negative 1, or whatever that divisor term is, by the number we drop down and add it to the next number. In this case, minus 1 times the 5 is minus 5. We then add a minus 5 to this next coefficient and drop down the result of that addition. So here we have minus 11. We do the same thing again. In this case, we'd have, I can just draw it out actually. Minus 11 times 1 is 11. 11 plus 3, we get 14. And then minus 1 times 14 minus 14, we get 0. You have a perfect factor if that's 0, because that's your remainder term at the end. How to interpret the answer? These coefficients here, you can write as the coefficients to your resultant polynomial. And you're going to notice that, for example, this top row, the big polynomial, is of degree 3. This thing should be of degree 2. So you got to shift all your exponents over 1 and write the answer. Okay, cool. And yeah, I think the advantage of long division is you can make it work for degree 2 or larger divisors, but I'm not at least aware of a way to do synthetic division for anything larger than a binomial. So just like x plus 1 or something like that. So this might be easier for that case too. So it's useful to know both. Okay. Last thing we'll touch on, and I must have either totally forgotten all the math I learned in high school, or my teacher just genuinely didn't cover this. But the rational root theorem is when you're trying to factor a polynomial of degree 3 or higher, you can, before you do any kind of factoring, use any kind of method, you can find all of the possible candidate factors that you have to work with. So what I mean by that is you can give yourself a bank of numbers to actually go through and test out and see if any of them are actually factors. And you can rule some out straight away. Okay. So what am I actually talking about? Well, if we have a polynomial like this, where we have some coefficients a sub some number, where a sub 0 is the constant term at the end, and a sub n is the leading x to the n term, then we take just these two coefficients, a sub 0 and a sub n, and we take, I think this should say n, oops. We take all of the factors of a sub 0 and a sub n, and then one by one we systematically divide all the factors of a sub 0 by a sub n. That will give us all of the possible zeros that we can consider as candidates when we try and factor. So, and that's just candidate options. It doesn't mean these are all the zeros. We didn't just find a magical way to find all the zeros super easily. We just know that these might be zeros. And if a number doesn't appear using this method, it will not be a zero of this polynomial. Okay. So I think it's easier to see with an example. So we'll consider an example, this trinomial here, or quadrinomial here, where our A3 term is 2, and our A0 term is minus 12, as is written here. Now we want to find all of the possible factors of each of these numbers. And when we do this, we consider the positive and negative versions of these factors. So, for example, with 12, all of the numbers that divide into 12, 1, 2, 3, 4, 6, and of course 12. And we consider the plus minus versions of these as well. So there are 12 factors of 12. For the number 2, we just have 1 and 2. Plus or minus, we have 4 factors of 2. Now what we do is we take a0 and divide it by an for each individual a0 and each individual an. So what this might look like is something like this, where we get 1/2 from dividing 1 over 2. We get 1 from doing 1 over 1, 3/2 from doing 3 over 2, 2 from doing 2 over 1, 3 from doing 3 over 1, and we just move on up like that. We calculate all of the possible numbers that we can get from any combination of 2 of these. And then we throw a plus or minus at the front. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8 candidate options for the factors. And because we are considering the plus and minus versions, we actually have 16 candidate factors. I don't know about you, that doesn't sound very useful to me because that means we have to check 16 options, and we might not even find the factor until we've tried doing synthetic division 16 times. So is it always totally useful? Can't say it's always super useful. But sometimes when you have numbers with very few factors, this can be super useful because you already can narrow down, okay, maybe there's just like 4 options and it's really easy to test. So that is the rational root theorem. And then from that, you can start with 1. In this case, we start with positive 1 as our factor, which I guess would correspond to this, x minus 1. Then we would do synthetic division, see if we get a remainder. If we don't get a remainder, then we were right. X minus 1 is a factor. If we do get a remainder, it's okay. So we just move on to the next candidate. And we do that over and over until we get down to something that looks like this, a nice factorization. Okay. Does that make sense? That strat. How we feeling about that? And it's okay if not. I think we're going to, if not today, we are going to do an example tomorrow. But yeah. Okay. Let's do some polynomial stuff. Okay. First of all, we can't really do a lot if we don't know how to multiply polynomials. So let's just quick sanity check, see if we got our method down. I will just do B because I have faith that you guys can FOIL and do part A. So let's see, how would we write this efficiently? Well, we want to multiply them. We can distribute this binomial like so and split it up like that. So why don't we do this? So we have x times this whole trinomial plus 2 times this whole trinomial gives us 2x to the 4 plus 2x squared minus 3x plus 4x cubed plus 4x minus 6. After we do our multiplication, we're just gonna scoop everything. Oh my goodness. Someone's been in the waiting room. Sorry. All right, here you go. Sorry, Eileen. I hope you weren't in the waiting room for too long. Okay. we scoop together all the like terms. So there's just 1x to the 4. There's just 1x cubed. There's just 1x squared. And then we have 2 x's, so minus 3x plus 4x is just going to be x. And then that last constant term, 6. Okay. Cool. So we've seen that before. Just getting a warm up. Nothing too crazy. Let's go ahead and give long division a shot. Now that we're warmed up. So start with number 1. And I'll try and conserve space as much as possible so we can do 2 of these. But the solutions for whichever ones we don't get to are posted on the Discord. So feel free to check them out. X cubed plus 3x squared minus 10x minus 24 divided by x minus 3. Okay. So remember, with long division, our goal is to find something we can multiply this number by, specifically so that we could cancel this leading term. In this case, we're going to use the x to cancel the x cubed, so we're going to need a factor of x squared to multiply that leading term by. This is going to give us, so x squared times x gives us x cubed. X squared times minus 3x gives us minus 3x squared. And then we're going to subtract this from these first 2 terms. Now, if we've done everything right, those should cancel. Well, we've got to be really careful with signs here. We're doing a lot of subtracting negative numbers from positive numbers from negative numbers. So we got to be careful. And it's going to be 3 minus minus 3. So this is going to be 6x squared. Now, because our divisor, x minus 3, has 2 terms in it, we drop down 1 term and keep moving. Here, if we want to cancel 6x squared, starting with just an x, we'll need a factor of, we need the 6, and we're going to need 1 more x. So 6x times x is going to give us that 6x squared. And that will be a positive 6x, because we want a positive 6x squared to cancel. In the meantime, 6x times minus 3 is minus 18x. These guys are going to cancel, and we have minus 10 minus minus 18. Say x. So the positive 6x squared, this guy, comes from multiplying positive 6x by x, and we want that to be positive because we're subtracting it from positive 6x squared. And we know that a positive 6 minus a positive 6 is going to give us 0. That's how we choose the sign, so that we can make this term, this red term, the same as this other red term. Hopefully that made sense. Okay, we'll finish up now. We have 8x. We'll drop down this minus 24. Now, to cancel x with 8x, we just need a factor of 8. So 8 times x gives us that. 8 times minus 3 gives us minus 24. And we're good. 0 remainder. That means x minus 3 definitely is a factor. And by dividing, we get to this guy. Okay. Um, I think if we move on to the next topic, we may be a little pressed for time. So I think just to kind of see where we're at, I'd like to take the remainder of the section and maybe split off into some breakout rooms and work on these last two long divisions. Um, Rishi, you could probably set up the breakout rooms. We can probably split into how many people we got? Uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 people. So 3 groups, probably. And for the remainder of the section, we'll just have you guys work on some of those. Risha and I'll hop around and check on you guys' progress along the way.
All right, yeah. You guys are gonna get put into breakout rooms in now. Cool.
All right. Cool. Good luck.